available, but people are not really giving all the information for people to be able to manipulate that without problem.
But if you make a large REV by mirroring the images?
So there are many possibilities. I just this is actually this is still an open problem. So you may use some sort of effective theory. So you just make a larger system and just calculate the effective properties on inside that. There are still bias, or people are just reverting back to the original problem and introducing what is called permeameter conditions, either in a very simple case, but those boundary conditions do not handle properly anisotropy effects unless they are oriented along the axis of X or Y or Z. You can relax that by using what I call Bamberger condition, because one of the first papers using that was produced by Bamberger, but it's called a linear permeameter. So you just impose boundary conditions here, which are, this drawing should be on the right side here. So there are many things. You take time to develop all the possibilities, the advantages and drawbacks of things, but it's important to understand that this must be addressed, and do not use the things that are in the, I will not mention any code, but many software attached to image reconstruction. They do something which is not necessarily what you want to use for your particular system. So be careful about that. This is the message. The second message is, of course, about the side of the image you want to use. And that's a big problem because we have very accurate X-ray tomograph, but they don't make very big images. And that's an important concern, which is illustrated here. In the case of randomly distributed diffusivity, and what I will look at, I will look at the size, the evolution of the effective conductivity in the x-axis direction versus the ratio of the side of the averaging volume with respect to some correlation length in the system. And there has been a lot of stuff trying to understand what's going on here. And in general, this is what happens. If I take several images, I can do some statistical analysis. So let us take a small volume. I will essentially have that gray figure here. Large variance for the effective permeability calculated, and the expectation will be something like that. And what happens is that if I increase the ratio size of the volume versus the correlation length, then in general the variance decreases, and at the end, of course, the variance is so small that you only solve over one picture, and you are pretty sure that you have something which is representative of your medium. But this is not always the case for when you use X-ray images, because most often we are somewhere in between here. So if you want to use your results, you have to work on the statistics of that. This is one important property for those upscaling problem, which I would like to mention. So now let us go to more complicated problem. And the first one of interest is the transport of a chemical species, and I will do that only in this short lecture on the tracer case. But there are results available for more advanced problem, including, for instance, the use of Stefan Maxwell equations or things like that. So this is very simple, but the methodology can be applied to a more complicated system. So in that case, I have the Stokes equation, the total mass balance, and essentially that which is added to the problem discussed by Professor Pillai some time ago. So the advection diffusion equation and the particular boundary condition here. I will first start with passive, which is called passive dispersion. So the flux of the chemical species is zero at the interface between the beta phase and the sigma phase. And I will use that methodology, upscaling methodology, I just summarized before on the simple case. So first, let us do the averaging of the transport equation here. So I will use the averaging transport theorem for the divergence, for the gradient. I will introduce the deviations, and I will use the approximations which have been discussed before. And if you mix all that, you get the following results. So you get an accumulation term which is already under a closed form. This is typical here of problems. Remember that when we average, we have two possibilities. We have intrinsic average. So if there is a buildup of concentration, there will be accumulation because the concentration here changes. But that might be also accumulation for the porous volume because of change in the porosity. So those dual effects are ubiquitous in all porous media physics. The averaging of that is split in two terms. One which is a macro scale advection term, and then something here which in the end will produce a dispersion, the dispersion term in the final macroscale equation. Here I have something which is equivalent to what has been introduced by Professor Pillai for the pressure. So I have both this macroscale stuff plus this tortuosity term here. And so we need to determine, this has already been determined by Professor Pillai. So this is a given field in this particular case, because I made the assumption that I have a tracer, so density and viscosity do not change with the concentration. So this is a known field, and I have to determine this one and to be able to calculate that and to calculate that. So the second step is to find the governing equation for that, and I'll just remind you that the governing equation is just the original porous scale equation that I have tweaked a little bit, and to tweak that I have used that decomposition, and also I will use that equation to simplify a little bit the equation. This is where the assumption of a local constant porosity take place. This modification is essentially straightforward if you assume that locally all gradients or time variation of porosity are small. So you can extract that and get a governing equation for the average concentration, and that will be useful to do that. Actually, I have not written an equation. Well, I deleted too much slides apparently in the system.
Excuse me.
Yes.
The previous slide. Could you please go back to the previous slide?
Yes. Which one? This one?
Yeah. So the bottom equation, the second term, is it like?
The second term. Which one? This one?
Yeah. So that's being transported by superficial velocity.
You can. You have. Let me do that here. So you have to average that. You introduce whatever you want to introduce, but let us, for instance, introduce in which here this is the intrinsic velocity, and here the intrinsic concentration. If I do that, I have the average of U beta C beta, of course, plus there will be cross averages, like for instance U beta C beta theta plus U beta and then this final dispersion stuff. Here, must be reminded that when I do that, I have somewhere here the phase indicator, because I'm working here with fields which are only defined in the beta phase. Okay, so that's the correct description. And if I take that, using the approximation I have introduced before, I can extract that from the average. I get the average of gamma beta, which is epsilon beta. And I can write that under two forms. This one, or if I want, introduce the filtration velocity here. And the filtration velocity is actually that. So both, depending on what you are interested in, you may write that. That's a mathematics. So I have not written let me write the small scale equation. I took a lecture I made to von Karman, but I had many hours, and so I probably deleted too many slides. So the let me use that notation for the intrinsic. It's much straightforward.